Okay, so let's get started. So we were talking about Doppler effect and shock waves last time. So we saw a couple of cases where either the source of the sound or the observer was moving relative to each other, and we saw 4 different formulas last time. Okay, so this is the formula when the source of the sound is moving relative to the observer, and these two are the formulas where the source of sound is traveling. The observer is traveling relative to the source. Okay, so and we combined all the 4 formulas into this common formula. Okay, and depending on the scenario, whether the source is moving or the observer is moving, we choose different signs. Okay, so let's see an example how we choose the right signs. So here is a problem. So a siren of a police car at rest emits a predominantly frequency of 1600 Hertz. So that's the frequency of source. Okay, Fs. And what frequency will you hear if you are at rest? And the police car moves at 25 meters per second towards you. So we want to know the frequency that you perceive if the police car is moving towards you, okay, at 25 meters per second. So which formula do we use? So we have 4 different formulas, and we have this general formula, and we have rule to choose the signs. Okay, so this is when the source is at rest. Okay, so we choose this sign convention for the source at rest, and this is when the observer is at rest. And from the question we see that the source is moving, right? So we can eliminate this situation. So the source is moving, source is not at rest. We can eliminate that. And observer is at rest. Okay, so observer has the velocity or sound speed of 0. Now we need to think about the sign. Okay, we choose the minus sign in the denominator when the source moves towards the observer. So we need to think about whether the source is moving towards the observer or source is moving away from the observer. It's moving towards the observer, right? So that means we can eliminate this one. So that means we need to choose the minus sign in the denominator because the source is moving towards the observer. So this term will be 0 because the observer is at rest. Okay? And we need to choose minus sign here because the source is moving towards the observer. And then this is what we need to find. Okay? Frequency of source is 1600. Speed of the source is 25 meters per second, which is Vs. Now what is V? You guys remember what is V?
343.
Yes, so at room temperature, normal temperature, 20 degrees Celsius, the speed of sound is 343 meters per second. So I want you guys to try this one and see what you get. Okay, so we have F0 is original frequency of sound, and on the numerator we have 1 because V0 is 0, so 1 minus Vs over V. Okay. So let's plug in the numbers and see what you get. So you got 17 point or
1725.
725 hertz, right? So that's frequency perceived by the observer. Did anyone get the same answer? You got the same answer? Okay, so a couple of people got the same answer. So that's the right answer. Okay. Anyone has a question on this? Okay. And then, let's see. Let's look at this question. Okay. So you can answer this based on what your result. Okay. So look at your result and think about this question. Is that right? B? Is that higher? You saw that in this problem, the initial frequency was 1700, right?
16.
Sorry, 1600. And then you saw there is increase in the frequency because of the motion of the source. So yes, the right answer is B. Okay. Let's look at this one. This is asking about the wavelength, okay, not frequency. So when you move towards the source, what happens to the wavelength of the sound? Does the wavelength get shorter, longer, or doesn't change? So this one, actually, there's a typo here. It doesn't change. Okay.
Doesn't change.
Let's fix that. So which one?
C.
Why do you think it's C?
Because the observer is moving around.
It is
The
already
observer is
C.
moving, so he's not emitting the waves. The waves don't change in reference to the observer. Of course,
The wave doesn't change, but the perception changes, right? Whenever there is motion between the observer and the source, you guys remember there's a squeezing in the wavelength. So we saw this last time. So whether the source is moving towards the observer or observer is moving towards the source, the wavelength gets squeezed, right? If it is moving away from if they are moving away from each other, the wavelength gets wider. Okay, so the distance between one waveform to another waveform is wavelength, and you see when they are moving closer to each other, there is squeezing of the wavelength. So the wavelength is shorter. So what do you think about this one then? So there is relative motion between the source and the observer. How will it affect the wavelength? Shorter, longer? Shorter, exactly, yes. Shorter. So again, when they are moving closer to each other, the wavelengths get squeezed. That's how the wavelength is shorter. Okay? We talked about this last time briefly. So these are the wavefronts emitted by source, and the source is moving at different speeds. So in this case, the source is moving at the speed less than the speed of sound. Okay? So it's moving to the right, but the motion of the source is less than the speed of the wavefront. Here, the speed of the source and the wavefront is equal. Here, the speed of the source is greater than the speed of, so the speed of the source is greater than the speed of this sound or the wave. Okay. The last one is when the speed of the source is highly exceeds the speed of the source. I take it back, sorry. So in this case, look at this one. This is the source, okay, source of sound. So source of sound is way ahead of the wavefront. Okay, so the source is traveling much faster than the wavefront here. So when the source travels much faster than the wavefront, so the wavefronts at this boundary, they all meet each other, okay, and they add each other, forming something called shock wave. Okay? It forms a cone-shaped structure called shock wave structure. Okay? So that's what happens when the source travels much faster than the wave itself. Okay? So at these boundaries, the waves meet each other and then it forms a very strong wave. And if someone happened to be at the boundary on this part, the person will hear loud sound. Okay? So let's see the video on that. So this video will make it more clear. Okay, so let's just see this without sound. Seems like there's no sound. So this is the source when it's at rest. Okay, so the source is stationary here, not traveling, and that's the wave front emitted by the source. So again, the distance between two wavefronts is wavelength. Now you see the source is traveling towards the observer. So when the source travels to the right, you see the wavefronts will get squeezed. Okay, so the source is traveling at half the speed of the wave. So the wave itself is traveling, expanding, and the source is also traveling with the wave. But the speed of the wave is greater than the speed of the source. Okay, you see the wavelength here is longer than the wavelength here. So any person standing here will hear higher pitched sound. Now this time, the source will travel at same speed as the expansion of the wave. So they are moving to the right at the same speed. And when a person standing here hears the sound, he or she will hear a loud booming sound, which is called sonic boom. Okay, so now the speed of the source is greater than the speed of the wave. So this will travel twice as fast as the expansion of the wave. So that's ahead of the wave. Because it's traveling faster than the wave, so it's ahead of the wave. Now when you consider many of these waves, you will see it will form some kind of cone shape. Okay, so this is a cone-shaped wave, and the waves at these boundaries, this boundary and that boundary, they add up. And if a person happened to be at that boundary, then the person will hear a loud sound, which we call a shock wave. I wish you can hear the sound, but you can imagine that a person is hit by the boundary, the person will hear a loud sound. That could sometimes shatter glasses and destroy some structures also, because that boundary has lots of energy. Okay, so that's about the Doppler effect. Any question on that? Okay, so let me ask you this question. So what happens when two objects collide? You have learned this in Physics 1. You have two objects, in this case two cars. When they move towards each other and collide, what happens? What could happen?
Energy first.
Just think about the consequence. Okay? What happens after they collide?
The velocity decreases.
Velocity what?
Decreases.
You don't need to think about the velocity. Just tell me like what happens to the car. What happened to the cars?
You get smashed up together.
They will stop.
Yeah.
They will smash each other. So yeah, you guys are right. So there are two possible scenarios here. Okay, one is elastic collision. If it is elastic collision, they will bounce back, right? That's what you saw in your Physics 1. So if I show you this one, if they are hitting each other elastically, so here is elastic collision. that's the elastic collision. So they will bounce back. If it is inelastic collision, can you guys guess what happens? They get stopped, right? Right, like that. Or if one has greater speed, then they will move towards the one that has greater speed, along the direction that has greater speed. So for example, if this one has greater speed, then it will move along the same direction as the one that has greater speed. Okay. They get stopped and move along the direction that has greater speed. So, in the same way, what happens when two waves meet? So you have two waves. One is traveling from my left to my right, and other one is traveling from my right to my left. What happens when they meet at a point? Anyways, think of the consequence. What I mean is, you have a wave going from left to right, and you have another wave that is going from right to left. So when they meet somewhere here, what happens?
Energy.
So you don't need to think about energy or speed or anything. Just think about the consequence. What happens to the wave, physically, or just think about the consequence
They're equal.
of the.
Will go up.
They will go up. Is that right?
Yes.
Believe that? Why they go up? So you're right.
No, if they're equal, there's no other way.
Mm-hmm. So they need to add up, right? So the two waves, they add up and they form a bigger wave. Okay? So when two waves overlap, there is a bigger wave, which we call superposition principle. The superposition principle is when two waves are simultaneously present at a single point. So here, these two waves are present at the same point. Then the displacement of medium at that point would be sum of the displacement due to this wave and sum of displacement due to this wave. So that's the displacement, and that's the displacement here. So if you add these two displacements, you will get a bigger displacement here. Okay? So superposition principle is adding the two waves by adding their displacements. Now, the question arises, what happens afterwards? So let's answer this question. So same kind of scenario, but after a big wave is formed, what happens afterwards? So let's read the question. So each pulse continues as though they never met one another, or the rope. Sorry?
Would they cancel each other out?
They will cancel each other out, but they didn't cancel, right? They added each other, and you got big wave.
They invert.
They invert.
So not like common.
There's no option for that. We'll talk about that in a second, but for now, let's just think about three scenarios. And you said, what's your name?
Aaron.
Aaron. Okay, you said,
A.
huh?
A.
Okay, so you're saying A, each pulse continues as though it had never made the other one. Is that right? Just believe that? And that's the right answer, okay? So they will move away from each other as if they never met. Okay, so let's see the simulation for that. That's the right answer. Here. So they will just move away from each other. So wave 2 now is here, and wave 1 is now here. Okay, so let's see the simulation here. slowly. So we have two waves traveling towards each other. So they meet at a point. So they meet at a point here. So you have this wave, this orange color wave and blue color wave, and this wave has that height and the blue wave has that height. If you add these two heights, you get that height. Okay? If you add this height to that height, you get that height. So you're adding the heights at each and every point, and then you get this resultant wave. So that's the superposition. So you're adding two waves to get a bigger wave. Now, what happens after? So they will move away from each other, like they never met. So that's what happens. Okay. So the motion of a wave and motion of object is completely different. Okay. So objects, when they hit each other, they bounce back from each other, or they get stuck. But here it's a different story. Waves, they pass through each other, because wave is not a matter. Wave is only some kind of disturbance. Okay, so the behavior of wave is completely different from matter. So now, using the superposition principle, we can add any types of waves. So let's say we have two types of waves. One is this triangular wave, and this one is a rectangular wave. And they are moving towards each other at 1 meter per second speed. This is moving to the right at 1 meter per second. That's moving to left at 1 meter per second. So 1 second later, they will be here. This one will be here because it will travel 1 meter in 1 second. Okay? So that's speed. That means this age would be at 3 because it travels at 1 meter per second. So that's after 1 second. So this one would be at 3 here because it's traveling this way. So that's the wave. Okay? So the only point they overlap is that point. If there's no overlapping here, there's no overlapping here. Only that point. And this one, the height of this one is 0, and the height of this one here at that point is that. Okay? So you're adding 0 to that height and you get the same height. 0 plus this height is the same height. Now, where will this wave be in next 1 second or after 2 seconds? Where will this wave be? It's going to right. So 1 second later, this is here now. 1 second later, that will be at 4, right? It's just traveling to the right. It's like, so right now it's here. 1 second later, it will be here. Next second, it will be here. Next second, it will be here. So it's going to the right by 1 meter every second. Okay? So here is the wave after 2 seconds later. So that's the triangular wave. Again, we have two waves. Let me draw the individual waves here. So we have, again, two waves. One is this triangular, other one is rectangular. So this is the triangular wave. And we have, let's use a different color. We have this rectangular wave. Okay. Now you see there's no overlapping in this region. There is overlapping in this region. Now you need to add this green one with the red one. So if you add this point let's consider this to be 1. Okay, and this point, let's consider that to be, let's say, 0.2. So you get 1 plus 0.2 is 1.2. Okay, you get that point. If you add this point to that point, you get this point, higher point. And at this point, both the red and the green have the height of 1, okay, same height. So if you add 1 and 1, you get 2. Okay, so you get twice as high as individual ones. So that's the height. Likewise, you add this red one, height of the red one, and the height of this green one, you get that height. You add this point and that point, you get that. And that point and that point, you get that. Okay. So the resultant here is. So this is the resultant. So this thing is the resultant wave. So again, there is no overlapping here, so it is as it is, and this one also as it is. And because there is overlapping in this region, so the result of the overlapping is this part. Okay? So that's 2 seconds later. Now, at 3 second time, this is at 3 second time, this will move to 1 meter further to right, and this one will move 1 meter further to left. Sorry, the rectangular will move 1 meter further to left, and the triangle will move 1 meter further to right. So that's the triangle in 3 seconds, and this is the rectangle. Now you can do the same thing. So let's see the overlapping part. So that's the triangle. Okay. And let's see the green one. So that's the rectangle. So there is no overlapping in this part, so you don't need to worry about that. And there is no overlapping in this part. There is only overlapping here. Okay? So the triangle, the part of the triangle overlaps with a part of the rectangle here. So now you add point by point. So you add this red to that green, you get that point. You add this point to this green point. Let's say this is half 0.5. 0.5 plus 1 is 1.5. It's here. Okay? And then at this point, both the red and green have 1 meter height. So 1 plus 1 is 2. So that's that. Okay? So this is the result of the overlapping. Okay? So that means your resulting wave would look like, so nothing happens here because there is no overlapping. Nothing happens here, there is no overlapping. And starting from here, there is overlapping, so that's the resultant. Okay, and then that's the part where there is no overlapping. So that's the resultant wave after the superposition. Okay? And then in next instance, they will separate from each other and then move away from each other. So there are two types of interaction here, or overlapping here. One is where the two waves add to give a bigger wave, which we call constructive interference. Okay? So the term that we use for addition of the two waves is called interference. Okay? So this phenomenon is called interference, where the two waves add up. And when the resultant wave has bigger height than the individual waves, then it's called constructive interference. So this is constructive interference because the resultant wave has higher height than the individual ones. Now there is another type of interference where the resultant wave has smaller height than the individual ones. So that kind of interference is called destructive interference. Okay, so let's look at this example. So this wave is moving to the right and is moving to the left. So this is their position 1 second later. Again, here it is. Let me draw individual ones. So this is one on the left. Let's use a different color. So that's the one on the left. Okay, and we have one on the right. Let's use green color. So this is one on the right. So this part, there is no overlapping in this part, and there is no overlapping here. There's overlapping only in this part, okay? So you see this part. Between 3 and 4, there is overlapping. So this part overlaps this part. So you need to do the math here. So you subtract this part. This is a negative part, okay? So let's say this is 0.5, half the total distance, total height. And that's half the total height. So this is positive, that's negative. So positive half minus negative half is 0. So the resultant here is 0. Okay? Likewise, you subtract this part from that part, you get this part. Okay? So you see this line. This line is the resultant of interference between these two waves, okay? These two parts, the red one and green one. You are subtracting this green one from the red one, and then you get this line. So the resultant is that wave. Okay, so this part, that part, and that part. So that's the resultant. Now, let's look at time t equal to 1.5. Okay? At 1.5, the waves would be over each other. So this is one wave going from left to right, and this is the wave going from right to left. Okay? So they exactly overlap each other. So this part cancels that part because they are, one is positive, other one is negative. This part cancels that part cancels that part. So the resultant is a flat medium. Again, the values of height here is negative. The values of height here are positive. So you are subtracting this part from that part from that part from that part from that. So when you subtract the values, you get a flat line. And then at 2 seconds, this part would be here. That's the wave at 2 seconds. And this wave would be here. Now again, there is overlapping between 3 and 4 meters. That means this part and this part, they overlap. So you subtract this wave part from this wave part, you get this line. Okay, so the resultant is this one. Okay. And then in the next instant, they will just move away from each other. So let's look at this. So on your notebooks, I want you to draw the resultant wave at time equal to 3 seconds. So this one is moving to right, this one is moving to left. So first think about where they would be after 3 seconds, and then think about the overlapping, and think about the resultant wave. you can just draw a rough sketch. Okay? You don't need to draw a nice one. You can even just think without writing. Okay? Think about what would the waves look like. Wave look like. So I'll give you option. The options are whether A, B, C, or D. So think about which one. So who thinks it's A? No one. B? C? Okay, 1, 2, 3. Okay, 3 people think 4. Okay, so majority of you think it's C. Anyone D? No one D. So C. So this 2 will be at 5. Okay, in 3 seconds, because it will travel. This will travel 3 meters in 3 seconds. So it will be here, and this part, this 6 would be at 3. Okay, so this will be at 3, and this will be at 5. So they will. This one will be like that. Okay. So it will look like at 3 seconds. The waves will be like this. Okay, so that's one wave, that's another wave. So you need to add the waves point by point. Okay, so you add this point with that point, it will be a little bit higher. This point with that point, a little bit higher. And here we have same height, twice as height. And then this point with that point with that point, okay? And then that point. So that will be the result. Okay, so the right answer is yes, it's C. Okay, let's think about this one. This is destructive interference. So I have options for you. We have these ones, A, B, C, D. Do you have answer for that? I think it's B. Okay, who else thinks it's B? Anyone? It's B? Those who think B? Some are still working. So I can eliminate A. A is not right because they are not exactly same. So in order for you to get a straight medium, they need to cancel exactly at the same point. So they need to have same shape. And I can eliminate C also, because when you subtract this part from that, the resultant would be positive number, not negative. So you have everything negative here. So you should have some positive number, positive wave. So you can eliminate A and C.
B.
So seems like right answer is B. Yes. So you are subtracting the bottom triangular part from the rectangular part. So you have this rectangular part, you have this part, you are subtracting that from that, and that will result B. ask you one more. Let's see this one. And you have options here. So what do you think? Which one? A? What do you think? Is it A? Who else thinks it's A? Who else thinks it's A? So yeah, what? So A is the right answer. Any question on how to get the resultant waves from superposition of two waves? Okay, so then let's continue. We have a couple more minutes left. Now, so far we talked about free waves. Okay, so free waves are the waves where the waves do not see any boundary. Okay, they can travel freely on a medium. Now, sometimes the waves get trapped between the two boundaries. So in this case, this is the oscillator that produces the wave, and there is a boundary here. So the wave is trapped in these two boundaries. So when the waves get trapped in the boundaries, the waves are called standing waves. Okay? So standing waves are the waves that are trapped and cannot travel in either direction. So the wave cannot travel beyond that boundary or beyond that boundary. So this is a traveling wave. So basically in traveling wave, the individual points in the medium oscillate up and down. But the wave itself cannot travel to the right or to the left. Only the medium moves up and down. So this is the medium, a string, and the string is moving up and down, but the wave itself is kind of still. Okay? And it's called standing wave because the crest and troughs stand in place. Okay, so this is the crest, and that's the trough. Okay, so they will remain at the same point throughout the motion. So how the standing waves are formed? So you need to think a little bit about the superposition to think about how the standing waves are formed. So when the two waves meet with each other, they interfere constructively at some instant and destructively at some other instant. Okay, so for example, let me show you a simulation here. So here we have two waves. One is traveling to the left and another one is traveling to the right. Okay. So here, at this point, they interfere destructively. So one is up like this, and the other one is down like this. Here it's up, here it's down, up, down. So they cancel each other. Okay, in this instant. So there is destructive interference when they overlap oppositely to each other. So if I show you the resultant, that would be the resultant. Okay, if I perfectly overlap, you'll see a straight line here because there is destructive interference. Now, in some instances, they will add each other when they mask their shape. For example, so here they are exactly overlapping over each other. That means the red one will add the blue one. Okay, so the resultant would be a bigger wave. Let's see the resultant. That's the resultant. Okay. I think we are out of time, so we'll continue this next time. If you guys have any question, you can. I will still be here, so you can come and ask me questions. Have a great weekend.
Hey, actually, is it the worksheet 1.2 up? You said, is the second worksheet? Yeah.
Not yet. I'll post it sometime.
No, the hour.